Thank you very much. Yeah, thank you, all of you here, for this wonderful meeting so far. I've had a great time, great presentations. I really enjoyed it a lot. So now it's my turn. I would like to talk a little bit about my recent preprint on MPE. My name is Ronald Sladky. I'm a cognitive scientist from the University of Vienna. My day job is cognitive neuroscience. I mostly study the amygdala, previously mostly on fear, also anxiety disorders, clinical applications, and recently also more in the context of social cognition, for example, trust learning. So now I talk about MPE. And I address MPE particularly from the direction as a cognitive scientist. So for me, MPE is kind of an edge case of normal cognition, and it's actually a quite problematic edge case. Why? Because there's some theories that I really enjoy. So like Mark Solm's idea, he wrote this book, The Hidden Spring. Feelings are real, and we know about them because they permeate our consciousness from the origin in some of the most ancient strata of the brain. They irrigate the dead soil of unconscious representations and bring them to mental life. So in his book, and there are several papers also, he says that phenomenal experiences of feelings, they provide meaning for us. The phenomenal experiences are qualitative and not quantitative, which is a very interesting point. So you start basically with some reflexes that are just some kind of regulation loops, and then at some point you have qualitative consciousness, which is really peculiar, right? Phenomenal experiences arise, phenomenal experiences arise from a so-called hidden spring, as he calls it, the subcortex, so brainstem, nuclei, and other subcortical areas. Similarly, Claremans also talk about experience that they're relevant for our survival. They provide meaning for us. And also Anil Seth talks about interoceptive models. And so you see where this line is going. In all these explanations, you somehow have a self-model that has some kind of biological function. So it aids survival. This is the reason why we have this complex phenomena. So we have a very convenient ecological computational theory. And then along comes Thomas Elephant, and it stomps on it and breaks it, right? So how should we proceed? In cognitive science, we are quite resilient to elephant attacks. We know that elephants tend to break nice paradigms in cognitive science, like Rodney Brooks' paper, Elephants Don't Play Chess, which taught us a lot that cognition is not only about abstract reasoning, but actually the most important reason and function of cognition and intelligence is to have a body in an environment and to basically have adaptive self-control in this environment. So I hope that the new insights from the elephant actually can also help us to improve our model of consciousness. So I already argued that it breaks the idea of self-serving models of consciousness. It also breaks the idea of habitual generative model, because usually generative models are hierarchically high, laterally wide, and temporally deep. We'll get to that. But what kind of model architecture is actually needed for MPE? The elephant also appears to break active inference, because usually generative models are for action-oriented cognition, for adaptive Bayesian self-regulation, and epistemic Bayesian inference. But what is the alternative to these kinds of models during MPE? Remember, there are no actions there. And it appears as if the elephant might break even the free energy principle, because we want to have optimal Bayesian models. We do this by surprise minimization and by minimization of a quantity called variational and expected free energy. So if any, what kind of free energy minimization is done during MPE? So these are the questions that I would like to ask myself as a cognitive scientist. So let's look at some of the computational requirements. Let's unpack this weird terminology that I've been using. So let us assume we have a set of neurons, or it could be clustered neurons. So this blobs can be anything you actually like. But let's say we observe something going on, we can record some kind of signal, right? If we have several of those neural populations in parallel, we actually have a lateral width that allows us to encode different kinds of signal sources. So the more laterally wide your model is, the more things you can actually hold in storage in parallel. Then there's another dimension that I want to point out here. That's the hierarchical height of your model. So if you basically go up this hierarchy, if you have a recurrent neural network, for example, or whatever kind of process that is hierarchical, you encode different qualities about your signals. So you can actually create signals that are more and more and more abstract of what you actually want to model. So something that is very obvious also for the non-modeling people is that you have different temporal features. The higher you go up in a hierarchy, the more abstract it gets, the more stable it becomes over time, right? Then there's a third dimension that is very important for active inference model, and that's the temporal depth of your model. And so far, we basically talked about a kind of predictive system that would model the world as it is based on its current experiences and what would happen if there are no actions at all. But the temporal depth equips the model with the capabilities of simulating different counterfactual futures, right? So if the ultimate goal of your model is to minimize expected free energy, the model can then make the decision which of the actions to choose. And if action number 2, as it's simulated or anticipated, will lead to a minimization of expected free energy or prediction error, whatever name you want to use here in this context, this option can be chosen and it will turn out to be the optimal solution based on what you know at the moment. Okay, so this is basically the language I'm going to use now. So let's see what we need for MPE cognition. So usually we have a high lateral width, so we can remember many things. We have a high temporal depth. We can predict the consequences of potential actions. The hierarchical height always needs to be somehow adequate to model the data, and we do some kind of self-modeling. For MPE cognition, the lateral width should be low. The temporal depth should also be low. So this is for staying in the moment. This is something that we will discuss, and you will see it's a rather easy problem to solve. When it comes to hierarchical height, we already run into a harder problem because we add the problem of complexity. And when it comes to self-modeling, you will see this is the final challenge in section 4.4, and this is a real puzzle at the moment. To solve this puzzle, especially about self-modeling, let me also introduce you to some interesting new neuroanatomical background knowledge. How I'm doing with the time at the moment? 9 minutes. During 10 minutes, you have 10 minutes. Okay. So I worked in the amygdala so far. So what I was thinking about was basically a self-model that is regulated. The amygdala for me is a link between interoception and exteroception. Very much adaptive self-control, and this is also very much in line with the idea of Solms, who talks about subcortical cognition as the origin of consciousness. And there's a big shift nowadays going on in neuroscience. Lisa Feldman-Barrett, for example, she also advocates that we should pay more attention to the limbic system as being the top of the cognitive hierarchy. Recently, there has also been a rediscovery of the so-called dual origin hypothesis of cortical development. So it's an old theory that was rediscovered because of resting state findings that couldn't be explained otherwise. And this dual origin hypothesis makes the following assumption. So for cortical developments, there are 2 big expansion gradients. One is originating in the amygdala system. So we have to split up the amygdala into the central amygdala and the basolateral amygdala, because this is what neuroanatomists tell us, and also what functional findings tell us. And when we look at the central amygdala, we actually see that it already implements some kind of very simple approach avoidance system. So we have input from the olfactory system, and then the central amygdala is a kind of valence system, and then the output via the striatum. The basolateral amygdala is an expansion point. So it starts with very simple laminar structure, actually no laminar structure at all. And from there, it expands to an even greater detail of laminar structure. And three big gradients are going along the temporal lobe. So many people with neuroscience experience know the what pathway, for example. And it goes via the insular cortex up to the somatosensory cortex and to the ventral prefrontal cortex. But there's another expansion gradient, and that comes from the hippocampus via the cingulate cortex up to the more dorsal areas of the cortex. So it's actually a little bit more complex. If somebody has any questions, we can go back to it during the discussions. So what are now my neurocomputational predictions? So for richness and flexibility in perception action, you need lateral width. The brain is a fantastic organ. There's always some kind of intrinsic dynamics going on, and this is actually what dominates the brain. So focused attention means that we need to tune the generative model to specific task requirements. Inattention, on the other hand, increases the likelihood that other models dominate. This is what we know as mind wandering. So my neurocomputational hypothesis now for MPE is that different models are iteratively selected and optimized to avoid being stuck to a model where no optimization progress can be made. This can lead to boredom or frustration. And as the mind abhors a vacuum, there is always some kind of, emergent new thought that pops into your conscious experience. So the phenomenal feeling of unconstrained openness in MPE arises actually from what I would assume being more kind of a focused attention and not from open, unconstrained cognition in the form of mind wandering. And many meditation techniques actually require focused attention on interoceptive perception, like breathing, for example. So this would actually mean that we're suppressing alternative models at this case. The insula is important to know is not creating a static mapping of our body. It's very dynamic, and there's recent findings that show that. You can also read it up in the preprint for the literature. This is actually something that we could also then manipulate using for example, fMRI neurofeedback task, we could actually modulate the insular self-model. So if we understood that it's about focused attention, the next challenge will be to get this attentive attentional top-down effort away, because this could lead to the strong association with a self-model, an attentive self-model. And so we need to have a different way of actually tuning attention. So we had for 2, temporal depth. I argue that the MPE requires both focused attention and non-agency. And there's already great work by Helen Slachter's group. But there's a problem, and this problem is non-agency. This is a problem for active inference, because active inference is always very pragmatic and about actions. So what happens? So we have to do something different to the normal active inference model. What happens in doing these kinds of experiences? We have to shrink our temporal depth of the model. So we have to basically remain in the model. So this highly accurate self-model would only be optimal for a very short time. Think of the dark room problem in active inference. We know that agents would go out and explore again, but we have to suppress this. We have to suppress our idea of habitual and goal-directed actions. So what we could do actually as an intervention is we could help meditators or any experimental subject to downregulate the striatum using focused ultrasound stimulation. This is something that has been done already in a pilot study. So being basically in the moment and without making anticipatory predictions in the future actually could explain somehow the loss of time perception during MPE. So our next challenge is then that we need to look So how at the hierarchical structure, so that we add complexity to the model, but of course we cannot flatline. We'll see that what this means. So I said we need to add additional layers to our model, but at some point we actually won't encode anything anymore. It will be just a flat line. This brings us into a problem for those people who are free energy principle aficionados, because everybody knows in this field that the model is always looking to minimize complexity while maximizing accuracy. So this is actually something that we see from a derivation from the formalism. So you see it in line 3. It's about minimizing complexity while increasing accuracy. It follows from the free energy principle. So overcomplex model, they can only exist for a very short time. Ecologically speaking, if the brain basically models something that doesn't contain any information, it gets rid of this. It's a process known as synaptic pruning, for example. It makes the model sparse. It's more energy efficient this way. And the alternative to say, okay, during MP, the brain isn't just not doing free energy minimization, is also kind of a violation, because not being able to minimize free energy would actually be a very unpleasant state. Or it would even break our idea of what life is, according to this paper by Carl Friston, because life is always about free energy minimization. So this is a real big problem. How do we get this kind of flatlining self-experience into the model? And the solution for this is we do Bayesian model reduction, which is a complexity reduction. Helen also mentioned it in her paper. But the question is, I have to speed up a little bit. I like to talk about it a lot. The problem is that we cannot do this. This is my argument in the self model, because the self model is too much constrained, basically our body and our bodily inputs. So I'm looking for an additional system next to the self model in the brain where this kind of model reduction takes place. A potential mechanism could be then this hippocampus system. So in system A, I assume that this kind of optimization model reduction cannot take place, because it's constrained by the bodily input. But in system H, in the hippocampus system, we have actually a working space where there are more degrees of freedom for model optimization, where such a thing can actually go on. And there's already some evidence for model reduction in the hippocampus. This is something that happens on a regular basis. Could also have something to do with, creativity and finding new solutions for problems. But the last problem that I'm going to address now, and you will see that the hippocampus system could provide a solution, is the self-identification with the model that you are having. So this is the final boss fight that we have now. We have to somehow get the self out of the self model. So the generative model is perspectival usually. It describes the computation that needs to be implemented for the agent's self-regulation. Likewise, the phenomenal model exists for someone, the agent, to do something, self-regulation. This is my cognitive science view on that. So we need the self-model to be stable in focus. We need it attenuated and well-regulated, and at least temporarily overcomplex. And if free energy minimization is still an imperative, the model needs to increase accuracy and decrease complexity somewhere else, outside the self-model. And I argue the hippocampus is the region where this happened. I suggest the existence of a neurocomputational model outside or parallel to the egocentric self-model, where free energy minimization happens during MP. I propose the hippocampus and connected brain areas would be a candidate for these processes. One has to note that the lower hierarchical levels of the system H, so areas in the default mode network, need to also be suppressed. They shouldn't provide noise into the hippocampus structure. So what would happen then? It would also be supported by some EEG findings. And in conclusion, what I'm proposing here is that there is this habitual phenomenal experience on the left side. We see interoceptive inputs being processed by the interoceptive cells. and used to link it to exteroception and to action. So this is our normal way of being. The hippocampus sometimes also provides from a narrative self-model some new input and perturbation into the self-model if there's no interesting interoceptive data points being processed. But this is habitual cognition. During MPE, what I would assume is a completely attenuated self-model. Basically, all prediction error from the body is being explained away. As a consequence, because there are no prediction errors, the stratum could also be basically losing its influence. So there's fewer action tendencies. Perfect. And what would be left would be actually the hippocampus system. And if the narrative input from the narrative model is not coming in, no autobiographic memories, then what we should observe is only a complexity reduction in the hippocampus, a very subtle feeling that we usually don't recognize. So we have a hidden spring and an endless ocean, or maybe a grumpy philosopher from Frankfurt was right. There's will and representation, or a more active inference perspective would be will and wonder, because it's an active process. I would like to thank you for your patience, and yeah, talk to you later.